All right, so we're diving into this paper today by Bezukhovnikov, Finkelberg, Kazdan, and Morton Ferguson.
Okay.
Modular reduction of complex representations of finite reductive groups. Wow, that's a mouthful.
Yeah, it's a fascinating area. We're essentially exploring what happens when you take a representation of a finite group, something defined over the complex numbers, and try to reduce it modulo a prime number, p.
Okay.
It's like translating a beautiful, intricate tapestry into a more simplified, pixelated form.
I like that analogy.
Yeah.
So we're trying to understand how these representations transform when we shift from the world of complex numbers to a finite field.
Right.
What's the history behind this idea of reduction mod p?
So the concept actually goes back to the 1940s.
Oh, wow.
With Brouwer and Nesbitt.
Okay.
And they pioneered a method for reducing complex representations of finite groups modulo p, resulting in representations over a finite field. Think of distilling the essence of the original representation into a simpler form.
Okay, that makes sense. So Brouwer and Nesbitt provided the foundation, but then Lusztig came along and focused specifically on reducing unipotent representations of finite reductive groups, right?
Exactly.
Why are these unipotent representations so special?
Well, unipotent representations are particularly interesting because they capture essential information about the structure of these groups.
Okay.
And the challenge Lusztig tackled was understanding the character of the resulting representation after this reduction mod p.
Okay.
This character tells us a lot about the representation's fundamental nature, but there wasn't a clear formula for it at the time.
And that's where this paper comes in, right? They actually prove Lusztig's conjecture and provide that missing formula.
That's exactly right, yeah. And this formula is a powerful tool enabling us to compute the reduction mod p of any unipotent representation of GF sub, where Q is a power of p. It's a significant breakthrough.
Wow. Before we delve deeper into the proof, could you remind us what makes finite reductive groups so important in mathematics?
Sure. So they're essentially the finite counterparts of algebraic groups, which are defined by systems of polynomial equations.
Okay.
Finite reductive groups appear in diverse areas of mathematics, from number theory and geometry to even physics. They possess a rich structure that makes them both fascinating and challenging in study.
And their associated Weyl groups play a crucial role here, right?
Yes.
I remember you mentioning something about near-involutions and Kazdan-Lusztig cells as well.
Right.
How do those fit into the picture?
Excellent question. So Weyl groups act like symmetries for these finite reductive groups. Think of them as transformations that leave the group structure essentially unchanged. Now, near-involutions are specific elements within the Weyl group. They're almost their own inverses.
Oh, okay.
And Kazdan-Lusztig cells provide a way to organize the Weyl group based on the behavior of its elements and their representations.
So these cells help us understand the relationships between different elements in the Weyl group.
Absolutely.
That seems pretty important for studying representations.
Absolutely. These concepts are crucial for analyzing the structure of representations. And there's another important player here, the asymptotic Heck algebra. It's a powerful tool for studying representations of Weyl groups, and it plays a key role in Lusztig's conjecture.
Okay, so we've got our finite reductive groups, their Weyl groups, these intriguing near-involutions, and the Kazdan-Lusztig cells. It sounds like a lot of moving parts. How do the authors of this paper actually put all these pieces together to prove Lusztig's conjecture and find those elusive sub-sub elements?
So their approach is quite ingenious. They begin by focusing on the module of regular functions on a torus. Think of it as a space where you can define polynomial functions.
Okay, I'm following so far. So they're working with these polynomial functions. What's the next step?
They construct a new basis for this module called the KLS basis by cleverly modifying the existing Steinberg basis.
Okay.
This new basis possesses specific properties that make it easier to perform calculations and connect them in sub-sub elements to the reduced characters.
That sounds pretty clever. What are those specific properties that make the KLS basis so useful?
One crucial property is W invariance.
Okay.
It means the basis elements transform predictably under the action of the Weyl group, simplifying our analysis.
That makes sense. So they've got this new basis that behaves nicely with the Weyl group. What's next?
This is where things get elegant. They introduce a standard pairing on the module of regular functions using the famous Weyl character formula.
Okay.
This formula connects characters to weights and plays a central role in representation theory.
Okay, and I'm guessing they use this pairing to link the KLS basis to its Boole basis.
Precisely. This link turns out to be crucial for defining those M-sub-sub elements, which are the building blocks of that character formula we've been after.
Wow, it's incredible how all these seemingly disparate concepts come together. You also mentioned the Duflo involution earlier.
Right.
How does that fit into the puzzle?
The Duflo involution is a special element within each Kazdan-Lusztig cell. Think of it as a representative of that cell. And it's crucial for constructing the M sub sub elements.
Okay, so we have the KLS basis, the pairing, and the Duflo involution. How do they finally use all this to prove Lustig's conjecture?
They show that the trace of its specific endomorphism, which captures the essence of the reduction mod process, is directly linked to the M sub sub elements in the character we want to calculate.
Okay,
It's like they found a way to translate information from the complex world to the finite field world using these tools.
that's remarkable. It seems like they've really achieved something significant here, but I recall from the abstract that Lustig had additional conjectures about the M sub sub elements, and those didn't always hold up, right?
Yes, that's right. Lusztig initially observed some intriguing patterns in his calculations, but it turns out those properties don't always hold true in more complex cases. For example, he conjectured that the M sub sub elements would always represent actual representations, meaning they could be expressed as a non-negative combination of irreducible representations. But the authors found examples where this doesn't hold, where the M sub sub elements are actually virtual representations.
Virtual representations, meaning they can have negative coefficients.
Yes.
That's fascinating. So even though some of Lustig's conjectures weren't entirely accurate, this paper helps us understand why those properties fail in certain cases.
Exactly, and that's the beauty of mathematics. Even when a conjecture is disproven, it opens up new avenues for exploration, leading to a deeper understanding of the underlying principles. It's about refining our knowledge and discovering new truths.
I'm also curious about the uniqueness of these meme sub-elements. Could there be other solutions out there that satisfy Lustig's conjectures?
That's a great question. The paper addresses this by exploring the concept of gamma-close collections, alternative solutions that might satisfy Lustig's conditions but differ slightly from the M sub sub elements they constructed.
Gamma-close means these alternatives would have to be very similar to the original sub-sub.
Exactly. They can vary, but only within specific bounds.
Okay.
And what the authors found is that while there might be alternative solutions, they wouldn't be fundamentally different from the sub-sub elements. They proved that adjusting the M sub sub elements to restore those failed properties, like positivity, is simply impossible.
So they've really nailed down these M sub elements. They proved Lustig's main conjecture, provided explicit formulas for these elements, and explained why some of the additional conjectures don't hold.
Yes.
It's remarkable. Is there anything else we can learn from these results? Are there connections to other areas of mathematics?
There is, and this is why things get really exciting. Remember those exceptional collections we talked about earlier, those objects from algebraic geometry?
Vaguely.
There's a conjecture that these collections, specifically one constructed by Samokin and Vender-Cullen, could provide another way to lift representations, potentially matching the lifts produced by the M sub sub elements.
Wait, so we might have two completely different paths leading to the same result. One using these abstract M sub elements and the other using geometric exceptional collections.
That's the idea. And the authors verified this conjecture in several lower rank cases, suggesting a deep connection between representation theory and algebraic geometry. It's like seeing two sides of the same coin, the algebraic side with the M sub sub elements and the geometric side with exceptional collections.
Wow.
This connection opens up a whole new world of possibilities, hinting at a deeper categorical interpretation of the entire reduction process.
A categorical interpretation.
Yeah.
That sounds fascinating. You're talking about category theory, the branch of mathematics that deals with abstract structures and relationships.
Precisely. Category theory provides a powerful framework for connecting different areas of mathematics, revealing hidden patterns, and unifying concepts. We might be able to use it to understand this reduction process at an even higher level of abstraction, potentially linking it to other, seemingly unrelated areas.
That's incredible. This deep dive has been quite a journey already. We've traveled from the 1940s to the present, explored complex representations, finite fields, Weyl groups, and even hinted at deeper categorical connections. But before we get lost in abstraction, can we take a look at some concrete calculations? The authors did some heavy lifting to compute those sub-elements, right?
They absolutely did, and while the general formula is abstract, the actual calculations can be illuminating. Lusztig had already manually calculated the M sub sub elements for similar cases like types A sub 1 sub, A sub 2 sub, B sub 2 sub, and A sub 3 sub.
And the authors of this paper confirmed Lusztig's calculations.
Yes, their formula produced the exact same results, which confirmed they were on the right track. They went further and calculated M sub sub elements for more complex cases like types B sub 3 sub and A sub 4 sub, which were significantly more challenging.
Can we look at a specific example to see how this works in practice?
Absolutely. Let's start with type A sub 1 sub, the simplest case, where the Weyl group has only two elements. We have two M sub sub elements, M sub 1 sub, which is simply V sub sub, the trivial representation, and sub 1 sub sub, which is V sub Q 1 sub.
Wait, what are those V's again?
Those V's represent characters of Weyl modules, a fundamental building block in the representation theory of algebraic groups. V sub sub is the character of the trivial representation, and V sub Q1 sub is the character of a Weyl module associated with a particular weight.
So even in this simple case, we see how the M sub elements can be expressed in terms of Weyl module characters.
Exactly, and as we move to more complex types, the calculations become more involved, but the principle remains the same. For instance, let's jump to type A sub 2 sub, where the Weyl group has 6 elements.
6 elements? Okay, things are getting more complicated. How many M sub sub elements are there in this case?
We have 6, of course, and they get increasingly intricate. For example, M sub 1 sub is, again, the trivial representation V sub 0 0 sub. But then we have M sub 0 1 sub sub, which is V sub Q 1 sub sub, and M sub 2 sub sub, which is V sub 0 Q 1 sub.
I'm noticing a pattern here. It seems like the single reflections in the Weyl group, like sub 1 sub and sub 2 sub, are connected to those V's with a Q1 in them.
That's a great observation. You'll see that pattern hold in other types as well.
Okay.
As we move to longer elements in the Weyl group, the formulas become more complex. For example, in type A sub 2 sub, M sub 2 sub sub is V sub Q dash 1 Q1 sub.
It seems like those Q1 terms are popping up everywhere. What about the other types? Did the authors compute those as well?
Yes, they provided tables with explicit formulas for types B sub 2 sub, G sub 2 sub, and even A sub 3 sub. They even used their algorithm to compute the M sub sub elements for types B sub 3 sub and A sub 4 sub, which were much more challenging.
Can we peek at those more complex calculations? I'm curious to see how intricate those NIM sub elements can get.
Of course. Let's look at type B sub 3 sub, where the Weyl group has 48 elements.
48 elements. We're definitely in the deep end now.
Indeed. The formulas get correspondingly more complex. For example, mem sub 3 sub, which is quite a mouthful, has the expression V sub Q1 Q2 sub plus V sub Q1 sub. We see those Q1 terms again, but now combined in more intricate ways.
Wow, that's a long string of V's. I can only imagine how challenging those calculations in type A sub 4 sub were.
You're right. Type A sub 4 sub has a Weyl group with 120 elements, and some of those M sub calculations were demanding, but the authors managed to do it. It's quite remarkable how they were able to explicitly calculate these M sub elements in such complex cases.
It really is. These calculations provide concrete examples of how this abstract reduction process works in practice. They give us a glimpse into the intricate interplay between representation theory and finite fields. But before we go too far down this road of examples, I want to back up for a moment and make sure we're clear about the key ideas behind the proof.
Sounds good. What did you want to focus on?
You mentioned the W invariance of the KLS basis and said it simplified the analysis. Can you explain exactly what that means and how it contributes to the proof?
Of course. Remember that we're working in the module of regular functions on a torus, denoted CT.
Okay.
This module has a natural action of the Weyl group W, which we can think of as permuting the coordinates of the torus. The Steinberg basis of CT is W invariant in the sense that the action of W permutes the basis elements.
Okay.
However, the authors actually need a basis of the W invariance of CT, which is the subring CT sub W sub, consisting of all the functions that are fixed by the action of W. So they modify the Steinberg basis to produce the KLS basis, which is a basis of CT sub W sub.
So the KLS basis is tailored specifically to work within the space of W invariant functions.
Right.
Why is that so crucial?
The W invariants of the KLS basis allow the authors to leverage the power of the Weyl character formula. This formula provides a way to express the character of a representation in terms of certain combinatorial data associated with the Weyl group. By working with a basis that respects this W action, they can directly connect the KLS basis to the characters of the representations they're studying.
That makes sense. It's like choosing the right language for the problem.
Exactly.
By using a basis that's aligned with the Weyl group symmetry, they can tap into the deeper structure of these representations. Is there anything else about the KLS basis that contributes to the proof?
Yes, there's another crucial aspect. The KLS basis elements are indexed by elements of the Weyl group W, just like the original Steinberg basis. However, the coefficients of the KLS basis elements, when expressed in terms of the Steinberg basis, involve certain polynomials called Kasdan-Lusztig polynomials. These polynomials encode subtle combinatorial information about the Weyl group and play a crucial role in many areas of representation theory.
So the KLS basis incorporates these Kasdan-Lusztig polynomials, which are already known to be important for understanding representations. How does this connection play out in the proof?
The presence of the Kasdan-Lusztig polynomials in the KLS basis allows allows the authors to relate the and sub-sub elements, which are defined in terms of the asymptotic Heck algebra, to the characters of the reduced representations. The asymptotic Heck algebra is intimately connected to the Kasdan-Lusztig polynomials, and this connection is exploited to establish a bridge between the algebraic world of the Heck algebra and the combinatorial world of characters.
That's fascinating. It sounds like the KLS basis is a bridge between several key concepts. It respects the W symmetry, incorporates the Kasdan-Lusztig polynomials, and ultimately helps connect the sub-sub elements to the characters of representations.
Exactly. It's a truly ingenious construction that lies at the heart of their proof. It allows them to work in a world where the well group action and the structure of representations are beautifully intertwined.
So by choosing the right basis, they gain a deeper insight into the reduction mod-top process and unlock the secrets of those subs elements.
Precisely. It's a testament to the power of choosing the right tools and understanding the underlying structure of the mathematical objects we're working with.
I'm starting to appreciate the depth of this work. It's not just about brute force calculations, but about carefully selecting the right framework and using it to reveal the hidden beauty of these representations.
I couldn't have said it better myself.
All right, so now that we have a good grasp of the foundation, I think it's time to delve into the heart of the proof and understand how they connect all these pieces together.
Absolutely. Let's do it. It's amazing how a seemingly simple idea like reducing representations modulo a prime number can lead to such a rich and intricate world of mathematical structures.
I completely agree. It's like we're peeling back layers of an onion, revealing more and more complexity and beauty with each step.
Yeah.
But I want to make sure I fully understand how these sub-elements are connected to the characters of the reduced representations.
Okay.
Can you walk me through that connection in more detail?
Absolutely. Remember that the sub elements are defined using the asymptotic Heck algebra,
Right.
which is a deformed version of the group algebra of the Weyl group. This algebra has a basis index by elements of W, and the multiplication in this algebra is governed by those Kasdan-Lusztig polynomials we discussed earlier.
Okay, I'm following so far. We have the sub elements living in this asymptotic Heck algebra. How do we get from there to the characters of representations?
The key insight is that the asymptotic Heck algebra acts on a certain module called the antispherical module.
Okay.
This module is closely related to the space of W invariant functions we discussed earlier.
Right.
And it carries important information about the representations of the finite reductive group.
So this antispherical module provides a link between the asymptotic Heck algebra and the representations we're interested in.
Precisely the sub-sub elements, as elements of the asymptotic Heck algebra, act on this antispherical module.
Okay.
And the way they act tells us a lot about the characters of the reduced representations.
Can you give me an example of how this works?
Let's consider a specific sub-sub element, say m_sub for some element W in the Weyl group. This element acts on the antispherical module, and we can compute the trace of this action.
Okay.
This trace turns out to be related to the character of the reduced representation corresponding to W.
So by analyzing how the sub elements act on this special module, we can extract information about the characters of the reduced representations.
Exactly. The trace of the action of sub encodes crucial information about the character values. It's like a fingerprint that identifies the corresponding representation.
That's incredible. It's as if the sub elements are carrying secret messages about these reduced representations, and we can decode those messages by observing how they act on the antispherical module.
That's a great analogy. It really captures the essence of what's going on here.
Okay, so we've established how these sub elements connect to characters. But you mentioned earlier that the sub elements themselves are constructed using the Duflo involution.
Right.
Can you remind me what that is and how it plays into this construction?
Certainly. The Duflo involution is a remarkable map defined on the Weyl group. It associates to each element W in W another element often denoted du sub, which shares several important properties with W.
Okay.
Crucially, the Duflo involution respects the Kasdan-Lusztig cells we discussed earlier. Elements within the same cell are mapped to each other under the Duflo involution.
So the Duflo involution provides a way to navigate within those Kasdan-Lusztig cells. Why is this relevant for constructing the sub elements?
The sub elements are defined using a specific basis of the asymptotic Heck algebra, and the Duflo involution guides the construction of this basis.
Okay.
To be more precise, for each element in W, the corresponding basis element is constructed using a combination of the standard basis element corresponding to W and the standard basis element corresponding to its Duflo involution, sub.
So the Duflo involution tells us which basis elements to combine to create this new basis of the asymptotic Heck algebra. And this new basis is what allows us to define the sub-elements.
Precisely. The do-flow involution plays a subtle but essential role in orchestrating the entire construction. It ensures that the resulting basis elements, and hence the sub-elements, have the right properties to connect with the characters of reduced representations.
It sounds like a carefully choreographed dance where the do-flow involution acts as the choreographer, guiding the movements of the basis elements to create this beautiful and intricate structure.
I love that analogy. It perfectly captures the elegance and precision of this mathematical construction.
I'm starting to see just how deep and interconnected this work is. It's a testament to the power of abstract algebra and the ingenuity of these mathematicians in using it to unlock the secrets of these representations.
Absolutely. It's a beautiful example of how abstract ideas can lead to concrete and powerful results.
Speaking of concrete results, let's shift gears a bit and revisit those explicit calculations you mentioned earlier.
Sure.
I'm still curious about those more complicated cases, like type B sub 3 sub and A sub 4 sub.
Okay.
Can you walk me through some of those examples in more detail?
Of course, remember that the authors provided tables of explicit formulas for the sub elements in those cases.
Yes.
These formulas can be quite intricate, involving combinations of Weyl module characters with various coefficients.
Yes, I remember seeing those long strings of V's with Q1 terms and more complicated coefficients. It looked pretty daunting.
It can be daunting at first glance, but there are patterns and structures hidden within those formulas.
Right.
Let's look at an example from type B sub 3 sub. Consider the element sub 2 sub in the Weyl group.
Okay.
The corresponding M sub element has the expression V sub Q1 Q2 sub plus V sub Q1 sub.
Okay, so we have two Weyl module characters, both with those Q1 terms you mentioned earlier.
Right.
What can we glean from this expression?
First, notice that both Weyl modules have a weight with a Q1 in the first position.
Okay.
This reflects the fact that the element sub 2 sub.
Okay.
This reflects the fact that the element sub begins with a reflection sub 2 sub. As you observed earlier, those single reflections often lead to Q1 terms in the corresponding Weyl module characters.
That's right. I remember that pattern. It's interesting to see how it manifests in these more complicated examples.
Exactly. Now, the second weight in each term also tells us something interesting.
Okay.
The first term has a Q2 in the second position, while the second term has a Q1. This difference arises because the element sub 2 sub 3 sub involves both sub 2 sub and sub 3 sub. The interplay between these reflections leads to the different exponents in the weights.
So the structure of the Weyl group element is reflected in the weights of the corresponding Weyl modules. It's a pretty neat connection.
It is, and authors exploit this connection to develop their algorithm for computing the M sub elements by understanding how the structure of the Weyl group element influences the weights of the associated Weyl modules. They can systematically determine the expressions for the M sub elements.
This is really starting to make sense. It's like they've cracked the code of these representations by understanding the intricate dance between the Weyl group, the asymptotic Heck algebra, and these Weyl modules.
That's a great way to put it. They've uncovered a hidden language that governs these mathematical objects, and by mastering that language, they can predict and understand their behavior.
I'm really enjoying this deep dive. We've covered so much ground already, from the historical foundations to the abstract algebraic framework and now these concrete calculations. But I remember that Lusztig made some additional conjectures about the TIM sub-elements that turned out not to be true in general.
Right.
Can we delve into those failed conjectures and see what we can learn from them?
Absolutely. Those failed conjectures are just as illuminating as the successes. They highlight the subtle and sometimes surprising nature of these representations.
One of the conjectures was about the positivity of the TIM sub-elements, right? Lusztig initially thought that they would always represent actual representations, meaning they could be expressed as a non-negative combination of irreducible representations. But the authors found counterexamples.
Exactly. In some cases, the sub-elements turned out to be virtual representations, which means they can have negative coefficients when expressed in terms of irreducible representations. This was a surprising discovery that challenged our initial understanding.
Can you give me an example of such a counterexample?
The authors found a specific counterexample in type a sub 4 sub for the Weyl group element sub 2 sub.
Sub 2 sub, the corresponding M sub element when expressed in terms of irreducible representations has a negative coefficient.
So even in this relatively simple case, the positivity conjecture breaks down. That's fascinating. Do the authors offer any insights into why this conjecture fails?
They do. They delve into the structure of this specific M sub element and explain how the geometry of the corresponding flag variety leads to this unexpected negativity. It turns out that the representation associated with sub-2 sub is related to a certain perverse sheaf on the flag variety, and the properties of this sheaf force the m-sub-sub element to have a negative coefficient.
So the geometry of the flag variety is playing a crucial role here. That's a connection I hadn't anticipated.
It's a beautiful connection that highlights the interplay between representation theory and geometry. The authors show that understanding the geometry of flag varieties can provide deep insights into the behavior of these representations. It's amazing how everything seems to be intertwined in this area of mathematics. The algebra, the combinatorics, the geometry, it all comes together to paint this intricate picture.
I couldn't agree more. It's a testament to the unity and depth of mathematics.
Before we move on, can you remind me what a flag variety is and how it relates to these representations? I'm a bit fuzzy on the details.
Certainly, a flag variety is a geometric object associated with a group. In this case, we're considering the flag variety associated with our finite reductive group. Roughly speaking, a flag is a chain of subspaces of a vector space, and the flag variety consists of all possible flags.
Okay, I remember hearing about flags in linear algebra, so the flag variety captures all the possible ways to arrange subspaces within a vector space.
Exactly. And it turns out that the geometry of this flag variety encodes crucial information about the representations of the group. The representations we're interested in can be realized as spaces of functions on this flag variety, and the way these functions transform under the group action determines the properties of the representation.
So the flag variety provides a geometric stage where these representations play out their roles. That's a fascinating perspective.
It is, and the authors exploit this perspective to explain why the positivity conjecture fails in certain cases. The geometry of the flag variety imposes constraints on the representations, and these constraints can sometimes lead to those unexpected negative coefficients.
It's like the flag variety is whispering secrets to these representations, and those secrets can be both beautiful and surprising.
I love that imagery. It really captures the essence of this connection.
This has been an incredibly enlightening discussion so far. We've explored the intricate connections between representations, Weil groups, Heck algebras, and even flag varieties. I'm beginning to see the elegance and depth of this area of mathematics, but I know there's still more to uncover. What other aspects of this paper do you think are worth exploring?
Well, there's one aspect we haven't touched on yet that really highlights the interconnectedness of mathematics, the connection to exceptional collections.
You mentioned them earlier, but we got a bit sidetracked with all the details of the KLS basis. I'm still fuzzy on what they are and how they relate to this whole story.
Right, so let's take a step back. Exceptional collections come from the world of algebraic geometry, specifically the study of derived categories of coherent sheaves. They provide a way to decompose complex geometric objects into simpler building blocks.
Okay, so they're like a set of fundamental building blocks for understanding certain geometric spaces.
Precisely. And what's fascinating is that these exceptional collections can also be used to lift representations. It's like taking a representation defined over a finite field and lifting it to a representation over the complex numbers.
Wait a minute, isn't that the opposite of what we've been talking about? We've been focused on reducing representations, mod p going from complex numbers to a finite field.
You're absolutely right. It seems counterintuitive, but there's a beautiful duality at play here. These exceptional collections provide a way to reverse the reduction process, at least in some cases.
That's incredible. It's like finding a hidden staircase that leads back up from the basement. But how do these exceptional collections actually achieve this lifting?
It involved a delicate interplay between the geometry of the flag variety and the algebraic structure of the derived category. Exceptional collections provide a way to construct certain special objects in the derived category, and these objects can be used to build representations.
So by manipulating these geometric objects, we can create representations.
Exactly. It's a remarkable connection between seemingly different areas of mathematics. And what's even more fascinating is that there's a conjecture that these exceptional collections can lift representations in a way that's compatible with the m-sub-sub elements we've been discussing.
Wait, are you saying that these two completely different approaches, one using those abstract sub-sub elements from the Heck algebra, and the other using these geometric exceptional collections, could potentially lead to the same lifted representations?
That's precisely the conjecture. It's a bold and exciting idea that suggests a deep harmony between algebra and geometry.
This is blowing my mind. It's like finding a secret passage that connects two seemingly separate wings of a grand mansion.
I love that analogy. It really captures the sense of wonder and surprise that these connections evoke.
So has this conjecture been proven?
It hasn't been proven in full generality, but the authors of this paper provide compelling evidence in its favor. They verify the conjecture for several lower-ranked cases, showing that the lifts obtained from exceptional collections do indeed match the lifts produced by the m-sub-sub elements.
That's amazing. It's like they found several matching puzzle pieces, hinting at a complete picture waiting to be assembled.
Exactly. It's a tantalizing glimpse into a deeper connection that's still being explored.
I can't wait to see what future research reveals about this connection. It's like a treasure map leading to a hidden mathematical treasure.
I share your enthusiasm. It's a testament to the beauty and mystery of mathematics where seemingly disparate ideas converge to reveal profound truths.
Before we wrap up, I want to revisit a point you made earlier about how these results actually allow us to compute the reduction mod p of any unipotent representation. Can we walk through an example to see how this works in practice?
Absolutely. The formula connects the reduction mod p, denoted ROS, to the some sub elements and certain virtual representations called almost characters. Essentially, you take the inner product of the original representation A with these almost characters, multiply by the corresponding m sub, and sub them all up.
So the formula provides a recipe for breaking down the reduced representation into these fundamental building blocks.
Precisely. And since we have explicit formulas for those m sub elements, we can actually perform these calculations. Let's consider a simple example in type A sub 2 sub for the unipotent representation associated with the sign representation of the Weyl group.
Type A sub 2 sub, that's the one with the 6-element Weyl group, right?
That's the one. Now, the sign representation of this Weyl group is a one-dimensional representation where each simple reflection acts by -1.
Okay, I remember. So we want to see how this representation behaves when we reduce it mod p.
Exactly. Now, the almost characters for type A sub 2 sub are a bit involved, but luckily Lusztig already calculated them. They're expressed in terms of unipotent Deligne-Lusztig characters, which, as you know, are fascinating objects in their own right.
Let's not get too sidetracked. But I trust we have all the ingredients we need to compute the reduction.
We do. The formula tells us that the reduction of this sign representation is equal to a sum of 6 terms, one for each element of the world group. Each term involves taking the inner product of the sign representation with the corresponding almost character and multiplying by the corresponding m sub.
Okay, I can see how that would give us a concrete expression for the reduced representation, but I bet those calculations get pretty messy.
They can, especially as we move to more complex types. But the beauty is that the process is systematic. We have the formula, we have the m sub elements, and we have the almost characters. It's all there.
That's amazing. So this paper has not only proven a major conjecture and deepened our understanding of this reduction process, but has also given us the tools to compute these reduced representations explicitly.
Exactly. It's a remarkable achievement. It's opened up new avenues for exploring the world of modular representations and revealed deep connections to other areas of mathematics.
Well, I think our brains have had enough exercise for one day. We've explored the intricate world of modular representation theory, delved into the mysteries of reduction mod p, and even caught glimpses of a deeper connection to algebraic geometry. To our listeners, we hope this deep dive has sparked your curiosity and left you with a sense of wonder at the beauty and complexity of mathematics.
And remember, even when conjectures are disproven, it's an opportunity to learn and refine our understanding. There's always more to discover.
That's the perfect note to end on. Until next time, keep those mathematical minds curious. Okay, ready to dive into some representation theory. Today we're looking at a paper that tackles a problem that's been around for like 80 years.
Wow, 80 years. That's a long time.
It is. It's all about how to reduce complex representations of finite groups, modulo p, a prime number.
Ah, modular reduction. That's a classic problem. So what's this paper all about?
Well, it's called, get this, modular reduction of complex representations of finite reductive groups.
Okay, quite a mouthful.
Yeah, a bit of a tongue twister, but the math inside is, well, it's pretty elegant.
I bet. So who are the masterminds behind this paper?
It's by Bizrakovnikov, Finkelberg, Kazdan, and Morton Ferguson. And get this, they actually solved a conjecture by the legendary George Lusztig.
Oh, wow, Lusztig. Now we're talking. What was his conjecture about?
It was from back in 2021. He proposed a way to describe these reduced representations, but his formula had these mysterious terms, MW.
W. Sounds intriguing. What are those?
Nobody knew how to calculate them, like they were these missing pieces of the puzzle.
Ah, so this new paper finally figured them out.
Exactly. Bezrekovnikov and his crew cracked the code, found a precise definition for those MW. Is a big deal. Turns Lusztig's conjecture into a proven theorem, gives us some serious tools for understanding representations.
I'm impressed. So spill the beans. What exactly are these MW and how'd they manage to define them?
Well, the paper mentions something called the Kazdan-Lusztig-Steinberg basis, which sounds pretty intense.
The Kasdan-Lusztig-Steinberg basis. I've heard whispers of this. It's a powerful tool.
Okay, so can you break it down for us? What's the gist of it?
Well, imagine you're trying to understand the traffic flow in a city, right? You might break it down into individual streets and intersections.
Okay, I can see that.
This basis does something similar for representations. It's like a set of building blocks, that lets us deconstruct these complex mathematical objects.
Okay, starting to get the analogy, but can we go a bit deeper into this Kasdan-Lusztig-Steinberg basis? Like, what are the streets and intersections in this case?
Sure. So we start with a torus T for our group G, which is split over a finite field. Think of this torus as our coordinate system for the group.
Okay, torus coordinate system, got it.
And we have the whale group, denoted W. It acts on this torus, shuffling around those coordinates.
So like a set of rules for how to rearrange those coordinates.
Yeah, exactly. Now, the Kasdan-Lusztig-Steinberg basis, it's a way of expressing elements in the coordinate ring of T, denoted CT, but in a way that's compatible with the whale group's action.
All right, so we've got our coordinate system and a way to shuffle things around. But how do we actually build this basis? Where do we start?
It's a clever process. We start with another basis called the Steinberg basis. It's denoted O.
Okay, Steinberg basis, got it.
Each element in this basis, it comes from taking an element, W, from the whale group and acting with it on a specific element of CT. This element is tied to the fundamental weights.
Fundamental weights, another new term.
Think of them as special coordinate directions within our torus. They're carefully chosen. So they generate the entire weight lattice of our group G, like the building blocks for all possible weights, which, essentially label different types of representations.
Okay, so fundamental weights are important. Got it. But what's the problem with this Steinberg basis?
Well, it lacks a certain symmetry, you see, with respect to the whale group's action. And the symmetry is super important for understanding representations.
Oh, so they had to modify this Steinberg basis to create this Kasdan-Lusztig-Steinberg basis to get that symmetry.
Exactly. They combined it with another set of special elements, the dual Kasdan-Lusztig basis, to create the Kasdan-Lusztig-Steinberg basis denoted.
All right. So this blending of the two, that's what gives this basis its power.
Precisely. It allows us to capture the interplay between the geometry of the torus and the combinatorics of the whale group in this remarkably elegant way.
That's fascinating. So by using this specific basis, they were able to isolate those elusive MOWs and, actually define them.
Yes. And the formula they found, it's surprisingly elegant of you, involved an operation called Q. Think of it as stretching our representation. They pair this stretched object with another carefully chosen piece of the representation, and boom, MW pops out.
Okay, I'm starting to see the magic here. But hold on, the paper mentions that Lusztig made some further predictions about these MW, like having symmetrical dimensions and representing actual, not just virtual representations.
Right. Lusztig had some ideas about how these MWs should behave.
But it sounds like things didn't always go according to plan.
Well, you see, Bezrukhovnikov and his colleagues, they discovered instances where those predictions, well, they break down.
Like Lusztig was wrong.
Not exactly wrong, but maybe not completely right in all cases. Sometimes they found MW with unexpected asymmetry.
Asymmetry, huh? Interesting.
Or those that didn't actually correspond to actual representations. It's a good reminder that even brilliant minds like Lusztig can be surprised by the intricacies of math.
So even in this abstract world, there's still room for surprises.
Absolutely. There's always something new to discover.
Now, what about implications beyond this specific problem? The paper mentions connections to other areas of math, like exceptional collections and coherent sheaves.
Ah, that's where it gets really interesting.
Hold on, exceptional collections, coherent sheaves, those sound pretty complex.
They are, but they're also incredibly powerful tools. Imagine finding a secret passageway connecting seemingly separate rooms, right?
Okay, I like that analogy.
Exceptional collections, they're like specially chosen building blocks for geometric spaces, particularly those called flag varieties.
Right, those flag varieties we touched upon earlier.
And the authors suggest that their MW, they might actually correspond to elements within these exceptional collections, like a hidden link between representation theory and geometry.
Whoa, okay, so we're linking these abstract MW to the structure of geometric spaces.
In a way, yes. And those coherent sheaves, they're like tools to study the texture of those spaces. Just like different fabrics have different textures, different spaces have different sheaves that capture their essential properties.
Okay, so we're connecting these MW to the texture of geometric spaces using these special building blocks, those exceptional collections. That's quite a leap.
It is, and it shows how deeply interconnected mathematics really is. Concepts that seem abstract and unrelated can turn out to be intimately linked.
This is all incredibly fascinating. I'm ready to delve even deeper into those connections.
Let's do it. Welcome back. Now, before we get back to that Kasdan-Lusztig-Steinberg basis, let's take a step back and think about those MW for a second. I remember they were like the missing pieces in Lusztig's conjecture.
Right, and Bezrukovnikov and his co-authors finally defined them using this special basis. But one thing that struck me was, like, those MW weren't always what Lusztig had predicted, right?
Yeah, you're right. Sometimes they had this unexpected asymmetry in their dimensions.
Asymmetry. That's unexpected.
It is. Or sometimes they didn't even correspond to actual representations.
So, like, Lusztig got it wrong.
Not exactly wrong, but his predictions didn't hold up in every case. It's a good reminder that math, even at this level, can still surprise us.
I get even the grades can make mistakes. But hey, those mistakes, those unexpected results, they can be valuable, right?
Absolutely. They force us to re-examine our assumptions, to think about things in a new light.
So in this case, those discrepancies in Lusztig's predictions, what do they tell us?
Well, they highlight just how complex these MW really are and how deeply they're connected to these underlying geometric structures.
Okay, so let's talk about those geometric connections. You mentioned this secret passageway analogy, right? Linking these abstract MW to something called exceptional collections in geometry.
Exactly. Remember those flag varieties we talked about?
Yeah, those abstract ways to organize all possible flags, but with subspaces instead of, actual fabric.
Right. Exceptional collections, they're like these carefully chosen building blocks for constructing those flag varieties.
Okay, I'm following.
And what's amazing is that the authors suggest that their MW might actually correspond to elements within these exceptional collections. It's a pretty mind-blowing connection.
Whoa, so we're linking these abstract MW from representation theory to the structure of these geometric spaces.
Exactly. It's like finding a hidden bridge between these two seemingly separate worlds.
Now, you also mentioned coherent sheaves as playing a role in this connection. Can you unpack that a bit more? What are those, and how do they fit into this whole geometric picture?
Think of coherent sheaves as a way to study the texture of these geometric spaces.
Texture. Okay, this is getting interesting.
Just like different fabrics have different textures, right? Smooth, rough, silky, whatever. Different spaces have different sheaves that capture their essential properties, their texture, so to speak.
So these NW are somehow related to the texture of those flag varieties using those building blocks, those exceptional collections. I'm trying to wrap my head around this.
It is pretty mind-blowing, but it just goes to show how interconnected mathematics really is.
So the authors actually tested this conjecture, right?
Yeah, they did some calculations for specific groups like A2, B2, G2,
Right.
and their calculations supported this connection. It seems to hold up.
That's amazing. What about more complex groups?
Well, that's where things get a bit tricky. The computations for groups like B3 and A4, those are much more challenging.
So we don't know for sure if this connection holds up in those cases.
Not yet. It's still an open question. More research is needed.
Sounds like there's a lot more to explore, but for now, let's get back to the specifics of this Kasdan-Lusztig-Steinberg basis. We talk about starting with the Steinberg basis, denoted and then modifying it, right, to incorporate the dual Kasdan-Lusztig basis. Could you walk us through the actual steps involved? Like, how do we actually build this thing?
Sure. Remember, each element of the Steinberg basis, it comes from taking an element δu from the Weyl group and then acting on a specific element of CT that's connected to the fundamental weights.
Right, those fundamental weights that act as coordinate directions within the torus T. But I'm a little fuzzy on how those fundamental weights connect to elements of CT. Can you clarify that?
Yeah, that connection is super important. Each fundamental weight, let's call it LE, corresponds to a character of the torus T. And a character, it's just a function from the torus to the field of complex numbers that preserves the group structure.
Preserves the group structure, meaning?
Meaning the product of torus elements maps to the product of their images under this function. It's like a homomorphism.
Okay, so each fundamental weight gives us this special function on the torus, this character. But how do those characters relate to CT, the coordinate ring of the torus?
Well, CT is basically the set of all polynomial functions on our torus T. And those characters we get from the fundamental weights, guess what? They're actually elements of CT. Yeah, they form a special subset of those polynomial functions, the one that capture the linear structure of the torus.
Okay, so the characters bridge the gap between those fundamental weights and the coordinate ring. They're like these specific polynomial functions that come from our fundamental weights.
Exactly. Now remember, the wheel group acts on the torus, right? Shuffling those coordinates around.
Right, right.
Well, that action also affects CT. Each element of the whale group transforms those polynomial functions in a specific way.
So each element doubly from the whale group takes a polynomial function in CT and gives us a brand new polynomial function.
Precisely. And we use this action, combined with those special functions from the fundamental weights, to construct the Steinberg basis.
Okay, walk me through it. How does that work exactly?
Let's take a fundamental weight, WVLIA, and its corresponding character, which we'll also call BLIA. Now apply an element W of the whale group to this character. That gives us W rudder.
Got it. So that's like a transformed character.
Exactly. It's also a character of T representing a specific polynomial function on the torus.
And this W telling this transformed character, that's the element U in our Steinberg basis.
You got it. We do this for each fundamental weight and each element of the whale group. And that gives us our Steinberg basis. Ew.
So the Steinberg basis is like a collection of these transformed characters, showing us how the whale group shuffles those fundamental coordinate directions in the torus.
You got it. Each element, E, captures how a particular whale group element, W, acts on a specific fundamental weight.
Okay, that makes sense. But now we need to tweak this Steinberg basis, right? Because it lacks a certain symmetry that's crucial for understanding representations. Can you remind us what kind of symmetry we're talking about and why it's so important?
It's all about how those basis elements behave under the action of the whale group. Remember, our goal is to use this basis to understand representations. And representations are basically ways for our group to act on vector spaces. We want our basis to play nicely with those actions.
So we need a basis that's well-behaved under the whale group's action. But what does well-behaved actually mean in this context?
It means that if we take a linear combination of our basis elements and then act on it with an element of the whale group, we should still get a linear combination of those same basis elements. Like their span should be invariant under the whale group's action.
Okay, so the basis needs to respect the symmetry of the whale group. But the Steinberg basis, it doesn't quite do that.
You got it. And that's where the dual Kasdan-Lusztig basis comes in. It helps us achieve that desired symmetry.
Right, that other set of special elements you mentioned. So tell us more about this dual basis. What makes it so special? Why does it work?
The dual Kasdan-Lusztig basis, it lives in a different space, the Heck algebra of the whale group. And it's closely tied to the combinatorics and geometry underlying our group G.
Hold on, Heck algebra. Now we're getting really deep into abstract algebra. What is that, and how does it fit into all of this?
We're going deep, that's for sure. But this Heck algebra is important. Think back to the whale group. It captures the symmetries of our group G, right? Well, the Heck algebra, it's a way to deform the group algebra of the whale group.
Deform the group algebra. Okay, now I'm lost. What does that even mean?
It's like taking a geometric shape, like a square, and stretching or twisting it, but in a way that still preserves some of its essential properties.
So we're distorting it, but in a controlled way.
Exactly. We're taking the group algebra of the whale group and adding this new parameter, Q, that lets us track certain geometric information.
So Q is like a knob we can turn to control how much we deform the algebra.
You got it. And by adjusting this Q, we can capture different geometric insights. Now, the dual Kasdan-Lusztig basis, it lives in this deformed world of the Heck algebra.
Okay, so we have this Heck algebra, this deformed version of the whale group's algebra. And the dual Kasdan-Lusztig basis is hiding out in there. But how do we actually find this dual basis? What does it look like?
It's defined recursively using these things called Kasdan-Lusztig polynomials. They're indexed by pairs of elements in the whale group.
Polynomials again. They seem to be everywhere in this field. What's so special about these Kasdan-Lusztig polynomials?
They're pretty amazing, actually. They have these deep connections to the geometry of flag varieties and the representation theory of Lie algebras.
Wow, they sound important.
They are. They were originally introduced to understand certain representations of Lie algebras, but they've become central to modern representation theory.
Okay, so how do we use them to construct the dual Kasdan-Lusztig basis?
We start with the standard basis of the Heck algebra, the one with elements indexed by the elements of the whale group. Then, using those Kasdan-Lusztig polynomials, we do this series of transformations on those basis elements.
So it's like an algorithm.
Yeah, kind of. It waves together the algebraic and geometric information from those polynomials to create the dual Kasdan-Lusztig basis. It's denoted and it has some amazing properties.
Okay, so we finally built this dual Kasdan-Lusztig basis. How do we use it to modify our Steinberg basis? What's the last step to create that Kasdan-Lusztig-Steinberg basis?
We combine elements of the Steinberg basis with elements of the dual Kasdan-Lusztig basis using coefficients from those Kasdan-Lusztig polynomials.
So we're blending those two bases together.
Exactly. It's like a hybrid basis. And this hybrid, it's the Kasdan-Lusztig-Steinberg basis. We denote it.
Got it. That was a long journey. We went from the Weyl group to the Hecke algebra, explored this Kasdan-Lusztig-Steinberg basis, and it's also we can define those MW, right?
Right. It's all connected.
Can you walk us through how those MW are actually constructed using this basis? What's the formula?
It uses this special endomorphism of CT, denoted spore, and our Kasdan-Lusztig-Steinberg basis. Specifically, its dual basis. We define it as the pairing of form applied to a particular basis element, FW0D, with another basis element, FW0W.
Whoa. Okay, let's break that down. What's an endomorphism?
Think of it like a function that maps a set to itself, but in a way that preserves some of its structure. In this case, phi, it acts on CT. It takes a polynomial function on the torus and gives us another polynomial function.
So it transforms those polynomial functions, but what makes this particular endomorphism so special?
It's special because it's like an approximation of the Frobenius endomorphism.
The Frobenius endomorphism. Okay, another new term.
The Frobenius endomorphism, it's a fundamental concept in algebraic geometry. Think of it as like raising to the power p, where p is our prime number. But it's defined in a way that respects the algebraic structure.
So it's like a modular power operation.
Yeah, you could say that. And our phi, it's constructed to be compatible with the action of the Weyl group.
Okay, so we have this almost Frobenius's endomorphism, phi, and we apply it to a specific element of the Kasdan-Lusztig-Steinberg basis, FW0D. Remind me, what are W0 and D again?
W0 is the longest element in the Weyl group, the most complex transformation we can do. And D, that's a Duflo involution.
Duflo involution.
Yeah, it's a unique element in the Weyl group that minimizes a certain function. It has to do with these things called left cells.
Left cells. Sounds intriguing.
Left cells are a way to partition the Weyl group based on how its elements interact with the Kasdan-Lusztig basis. And a Duflo involution, it's the special element within its left cell. It's unique, and it has certain properties that make it important here.
Okay, so we take FWD, apply our almost Frobenius's endomorphism to it, and what then?
Then we pair this transformed element with another element of the dual Kasdan-Lusztig basis. It's FWW.
Pairing. What does that even mean?
It's an operation that takes two elements of CT and combines them to give us a complex number. It's a way to see how they interact on the torus.
Okay, so we pair those two elements, and that finally gives us our MW.
Exactly. That's the definition of MW. It's a complex number that tells us a lot about the representation being reduced modulo P.
Wow, that was quite a journey. From the Weyl group to the Hecke algebra to this Kasdan-Lusztig-Steinberg basis, and finally, this carrying operation that gives us MW. It's like a whole new language.
It is, and it's pretty remarkable how mathematicians have combined all these different concepts from algebra, geometry, and combinatorics to understand these representations.
So can you remind us why these MWs are so important? What role do they play in Lusztig's conjecture and our understanding of modular reduction?
Remember, Lusztig's conjecture was all about describing the reduction mod P of certain representations called unipotent representations. And his formula expressed this reduction as a combination of simpler building blocks called Weyl modules.
Right, those Weyl modules, like Lego bricks for building representation.
Exactly. And those MW, they're the coefficients in Lusztig's formula. They tell us how much of each Weyl module we need to construct the reduction mod P of a given unipotent representation.
So they're like the instruction manual for building those reduced representations using the Weyl module Lego bricks.
You got it. They're the key to understanding how it all works.
And now that we have a precise definition for MW, Lusztig's conjecture is officially a theorem.
It is. Thanks to Bezrikhovnikov and his colleagues, they provided the missing piece of the puzzle.
That's amazing. So now that we've gone through all this hardcore math, can you connect it back to our listeners? Why should someone who's not a mathematician care about this?
Well, representation theory is all about symmetry. And symmetry is everywhere, right? From the structure of molecules to the behavior of particles to even computer algorithms.
So understanding these MW, it helps us understand those fundamental symmetries.
Exactly. It's like having a new language to describe and analyze those patterns.
Okay, so it's not just abstract math. It has implications for the real world.
It does, and it just goes to show the power of pure fundamental research.
Now, one thing that really caught my eye was the discussion about the non-uniqueness of those MW. You mentioned that for some groups, like SLN, where n is greater than or equal to 3, there might be other objects that satisfy the same properties as MW, but are subtly different. Can you expand on that? What does this non-uniqueness mean, and what are the implications?
It's a really fascinating point. The non-uniqueness of those MW shows just how complex this problem really is, and that there might be multiple ways to look at it.
Multiple ways. So it's not just about finding the one true answer.
It seems not. It's more like exploring a space of possible answers, each with its own nuances.
So maybe each solution offers a different perspective on the underlying math.
That's a great way to put it. It's like having different algorithms for solving a problem. Some might be faster, some might be more elegant, but they all work.
So the best solution might depend on the specific problem you're trying to solve.
Exactly. It's about finding the right tool for the job.
Now, the paper goes into detail about this non-uniqueness for SLN. Can you walk us through some specifics? I'm curious to see how these alternative MW actually look and what makes them different.
Sure. Let's take SL3 as an example. The authors construct an alternative set of objects, denoted MW. They have the same properties as the MW, but differ in how they're expressed in terms of Weyl modules.
So these MW, they're like imposters, pretending to be the real MW.
Kind of. They have the same overall effect. They capture the same information about modular reduction, but their recipes are different.
Recipes?
Yeah, remember the MW act as blueprints for building representations using those Weyl modules as building blocks. Each MW has its own unique recipe reflecting the Weyl group element it's associated with.
So the MWs are like chefs, and the Weyl modules are the ingredients.
Exactly. Now for SL3, those MW, they have the same overall flavor as the MW, but they use slightly different combinations of those Weyl module ingredients.
So like two chefs making the same dish, but using different techniques or spices.
That's a great analogy. And the amazing thing is those alternative MW, they still work. They still satisfy Lusztig's conjecture. It just shows there's more flexibility in this mathematical framework than we might have thought.
More flexibility, huh? So maybe there's not just one right answer in math.
It seems that way. And this opens up all sorts of new questions. If there are multiple solutions, which one is the best? Or maybe each one gives us a different perspective on the underlying math. It's a lot to think about.
Well, this has been an incredible journey. We've delved into the Kasdan-Lusztig-Steinberg basis, uncovered the secrets of those MW, and even explored the possibility of multiple solutions to Lusztig's conjecture. It's been a wild ride.
It has, and the best part is this is just the beginning. There's so much more to discover in this field.
Okay, let's give our listeners a moment to digest all this incredible information. We've covered a lot of ground. When we come back, we'll continue our exploration of this paper, venturing even deeper into the world of modular reduction and representation theory.
Sounds good. See you soon.
Welcome back to the Deep Dive. We've been on quite a journey exploring this paper that proves Lusztig's conjecture and reveals these unexpected connections between different areas of math.
It's been mind-blowing, really. From that Kasdan-Lusztig-Steinberg basis to those MW elements, there's been so much to unpack.
Right. And one thing that really stood out to me was how this research goes beyond just, solving a theoretical problem. We talked earlier about how representation theory, especially the study of symmetry, it has implications for other fields too, right? Like physics and computer science.
Absolutely. Symmetry is fundamental. It pops up everywhere. And representation theory gives us the tools to really understand those symmetries.
So by understanding these MW and how they work with modular reduction, are we basically getting closer to understanding those fundamental principles that govern everything around us?
You could say that. It's like we're gaining a deeper understanding of the underlying structure of the universe.
Okay, so this research has implications beyond just pure math, but let's zoom back in on the paper for a minute. I wanted to revisit that concept of positivity. Remember, Lusztig predicted that all those MW would correspond to actual representations, not just virtual ones.
Right, he thought they'd all be positive, so to speak.
But the authors found some counterexamples, right?
They did, and those counterexamples, they raise some really interesting questions. Why do some of these MW not fit that positivity condition? What does that tell us about how they work?
It's like we've solved one mystery, but now we have a whole new one to figure out.
Exactly, and often those new mysteries are the most exciting ones to explore.
So where do we go from here? How do we solve this new mystery?
Well, one path might be to dig deeper into those geometric connections we talked about. Remember those exceptional collections and coherent sheaves?
Right, those give us a way to connect those MW to the geometry of flag varieties.
Exactly. Those flag varieties might hold the key to understanding why some W don't behave as expected.
It's like those MW are living in this hidden dimension of flag varieties. And maybe those that don't satisfy positivity, maybe they correspond to some really strange or unusual geometric features of those spaces.
That's a really interesting thought. It's like the geometry of those flag varieties is somehow influencing the behavior of those MW.
Now, the authors do admit that this connection to geometry needs more investigation, especially for those more complex cases like B3 and A4. Sounds like there's still a lot of work to be done.
There is, but that's what makes research so exciting. It's not just about finding answers, it's about opening up new avenues for exploration.
It's like we've been given a map, but it only takes us part of the way. We need to figure out the rest of the journey ourselves.
You've got it. It's all about using our creativity and intuition to push the boundaries of what we know.
Well, I think it's time to wrap up our deep dive into this amazing research. We've explored some pretty complex math, delved into physics and geometry. It's been a whirlwind.
It has, and I hope our listeners have a new appreciation for just how beautiful and interconnected mathematics can be.
I think they do. This research really shows the power of human curiosity, our drive to understand the world and our ability to solve these really challenging problems.
It's been a pleasure diving deep with you. I hope everyone listening keeps exploring and questioning and pushing their own understanding of the world.
That's what it's all about. This has been The Deep Dive. Until next time, keep those minds curious. 68i. All right, let's dive deep into some fascinating mathematics today. We're going to be talking about modular reduction of complex representations of finite reductive groups.
That's right. We've got some excerpts from a pretty exciting research paper that tackles a puzzle that's been around for quite a while.
Oh, I love those kind of mathematical mysteries. So what's the puzzle this paper is trying to crack?
It's all about how these really complex representations, you can think of them like ways to describe symmetries, behave when we change the mathematical world they live in. Like, imagine changing the underlying geometry of a system.
So we're changing the rules of the game, and we want to see how these representations adapt. What's this new world that we're talking about?
Think modular arithmetic, specifically reduction mod p. It's like working with a clock. One will only p hours on it. Once you go past p, you just loop back to the beginning.
So instead of our usual numbers, we're dealing with the remainders after we divide by a prime number p. Okay, I think I'm starting to get the picture. How does that apply to these complex representations, though?
Well, imagine these representations as intricate structures, but built from simpler pieces, right? Reducing them mod p is like focusing on just the essential building blocks that survive after this sort of arithmetic is applied.
So we simplify things but keep some core information. What kind of representations are we looking at specifically?
We're in the realm of unipotent representations of finite reductive groups. They're really rich objects that describe symmetries in certain algebraic structures.
Okay, I'm following so far. So the paper focuses on what happens to these representations when we apply this reduction mod p.
Exactly. How do they transform? How do their properties change? And what new insights can we squeeze out of this process?
And this is where a brilliant mathematician named Lusztig enters the picture, right?
Exactly. Lusztig had this conjecture. He thought there should be a specific formula to describe the character of these reduced representations. The character is basically like a fingerprint, capturing key information about the representation.
So Lusztig wanted a way to identify and classify these reduced representations based on their properties. Did he actually find this formula?
He proposed one, but it had these terms denoted as M and W that were not explicitly defined, like missing puzzle pieces, only known for a few specific cases.
So this research paper is all about finding those missing pieces, defining those elusive MW elements.
That's it. They dive deep into abstract algebra, particularly a structure called CT, which represents functions on a torus.
Wait, hold on. A torus, like a donut. And what are these functions on it?
Yes, you can think of it like a donut, and functions on the torus assign values to each point on the donut. CT represents all polynomial functions on this torus. It's a really important structure.
Okay, so we've got this space of functions on a donut. What are we doing with it?
They construct a new basis for this structure, denoted as CT, which is super helpful for analyzing the traces of certain operators.
Operators, what are those?
Think of them as transformations that act on these functions in CT. They're connected to the symmetries we're studying, and their traces give us information about their overall effect.
Got it. So by looking at the traces, we get insights into how these operators behave, which in turn tells us about the representations themselves.
Precisely. And this new basis they constructed gives them a powerful framework for this analysis.
Now, how do those MW elements fit into all of this? I remember you mentioned they're defined using this new basis and something called a pairing.
Right. A pairing is a way to combine two elements and produce a single value. It's like measuring how compatible two objects are. In this case, the pairing involves the Weyl character formula, a key tool in representation theory.
I'm starting to see the pieces come together. We have a new basis, this pairing idea, and the Weyl character formula all working to define those missing MW pieces. What does the formula actually look like?
Here it is. MW equals QFW0W FW0W. It's a compact formula, but there's a lot packed in there.
Can we unpack it a bit? What's Q?
It's an operation that raises the input to the power of Q. Q is a power of our prime P, so this ties back to the reduction mod P concept.
Bringing in that clock arithmetic we talked about. Okay, what about FWD and FW0W? Those look complicated.
Those are specific elements from their new basis. The choice depends on something called Duflo involutions.
Duflo involutions sounds a bit intimidating. What are those exactly?
They're special elements in the Weyl group, a group that describes the symmetries of a root system. You can think of them as distinguished representatives of certain sets of symmetries.
So they help us pick the right basis elements for the formula.
Precisely. FWD and FW0W are chosen based on these Duflo involutions, guiding us to the correct pieces.
And lastly, the symbol, that's the pairing operation, right?
Yes, it combines those transformed basis elements using the Weyl character formula.
So we pick specific basis elements based on Duflo involutions, transform them using Q, pair them together, and out pops the MW.
You got it. And what's remarkable is that this definition of MW actually satisfies Lustig's conjecture. It gives an explicit formula for the character of these reduced representations.
Wow, so they found those missing pieces and completed the formula, but it sounds like the paper doesn't stop there, does it?
Not at all. They go on to explore the properties of these MW elements, like whether they're unique, how they relate to other important concepts, and even some unexpected behavior.
This is already blowing my mind. I'm ready to dive into those details. Let's start with their properties. What's the first thing they investigate?
Well, they start by looking at how MW can be expressed in terms of Weyl modules, which are fundamental building blocks in representation theory.
Weyl modules, right? I remember we talked about those being essential ingredients in building up more complex representations. So they're saying these MW are somehow related to Weyl modules.
They proved that each MW can be written as a specific combination of Weyl modules. Understanding Weyl modules is key to understanding the MW and vice versa.
So the MW inherits some of their characteristics from these Weyl modules. What kind of combination are we talking about here? Is it simple or is it a bit more involved?
It can get quite intricate, actually. Lusztig originally thought the Weyl modules used to express MW would have weights very close to a certain weight related to MW, but it turns out that's not always true.
Very close in terms of their weights. What does that even mean in this context?
It means the difference between the weights of those Weyl modules and the specific weight tied to MW would be relatively small, bounded by a certain value. The researchers were able to confirm this part of Lustig's conjecture in some cases, even giving a specific bound on how much those weights can differ.
So they were able to quantify this notion of closeness, putting a precise limit on how much those weights could deviate. That's pretty cool. What else did they discover about these combinations?
Well, there's an interesting detail here. Lusztig initially conjectured that the combination would always involve positive coefficients, meaning each Weyl module would contribute in a positive way to building up the MW. But, well, it turns out that's not always the case either.
So Lusztig thought these MW would be built from Weyl modules in a sort of constructive, positive way, but that's not always true.
Exactly. They found examples where the coefficients are actually negative. It means that these MW sometimes involve a sort of subtractive combination of Weyl modules, which wasn't what Lusztig initially anticipated.
Wow, so even in this seemingly straightforward relationship between MW and Weyl modules, there are unexpected twists and turns. Where do they find these examples with negative coefficients?
In types B3 and A4, to be specific, it shows that this positivity idea, while intuitive, doesn't always hold up. These MW elements are full of surprises.
It's like they have a mind of their own, defying expectations. I'm starting to see why these MW elements are causing such a stir in the field. They're turning out to be much more intricate and nuanced than anyone initially thought.
Exactly, and we haven't even touched on the symmetry properties of their dimension polynomials or delved into the question of whether they're unique. There's still so much to explore.
All right, I'm on the edge of my seat. Let's dive into those next. What about these dimension polynomials? What did Lusztig conjecture about their symmetry, and did it hold up?
He conjectured a particular type of symmetry in these polynomials related to certain reflections in the Weyl group, but again, it turns out it doesn't always hold true.
So another one of Lusztig's conjectures bites the dust. What did they find counterexamples this time?
In type A4 specifically, they found an MW whose dimension polynomial breaks this expected symmetry. It really highlights that these MW don't always behave as neatly as we might initially assume.
It's like each step we take reveals another layer of complexity. It's fascinating, but also a bit daunting. But before we get lost in the weeds, let's take a step back and talk about uniqueness. What does it even mean for these MW elements to be unique? And did the researchers find that they were?
It's a great question. It means asking if their particular construction of MW is the only one that fits into Lusztig's conjecture. Could there be other ways to define MW that would also work? They looked into this specifically for the group SL, and which is a kind of matrix group.
So they're essentially looking for competitors, other potential solutions to the puzzle. Did they find any?
Their findings were pretty interesting. For SLN, where n is less than or equal to 5, they showed that if any other solutions exist, their dimensions can only differ from their MW dimensions by a constant.
So even if there are other solutions out there, they would be pretty similar to the ones the researchers found, at least in terms of their dimensions. That's pretty remarkable. Does that mean their solutions are the best ones in some sense?
Well, it certainly suggests that their solutions capture some essential aspect of the problem. And get this, in the case of SL5, they were able to completely rule out any other potential solutions that would satisfy all of Lusztig's conjectures.
Wow. So in a sense, for SL5, their MWs are the true solution to this mathematical puzzle.
Exactly. It's a powerful result that highlights the elegance and effectiveness of their approach.
This is incredible. We've gone from exploring this abstract concept of reduction mod P to diving into these intricate MW elements, uncovering their unexpected properties, and even proving their uniqueness in certain cases.
It's been quite the journey, and we're not done yet. Remember, we still have that fascinating connection to exceptional collections to explore.
I can't wait to delve into that. It sounds like we're about to uncover another layer of hidden connections in the mathematical universe.
You're absolutely right. This is where things get really interesting. Ready to jump back into those MW calculations, we were starting to unpack how the researchers actually found these elusive elements.
Absolutely. You mentioned they started with simpler cases, right? Like a warm-up before tackling the really complex stuff.
Exactly. They began by reproducing Lusztig's original calculations for types A1, A2, B2, G2, and A3, just to confirm that their general formula agreed with those specific results.
So like a sanity check, making sure their approach aligned with what was already known. What do these early examples look like?
Well, take type A1, for example. The Weyl group there is super simple. Just two elements, the identity and a reflection.
Okay, so only two M and W elements to compute in that case. What do they look like?
For the identity element, the MW turns out to be the trivial representation, the do-nothing representation. Pretty straightforward.
Makes sense. What about for the reflection element?
For the reflection, the MW is a one-dimensional representation where the group element acts by multiplication by Q1. Remember, Q is a power of our prime number P.
So even in this simplest case, we see that reduction mod P idea popping up with the Q1. What happens as we move to more complex types?
Things get more interesting, for sure. In type A2, for instance, the Weyl group has 6 elements, so we have 6 M and W elements to compute. The calculations get a bit more involved, but the idea is the same using their new basis and the Weyl character formula.
Do we start seeing those linear combinations of Weyl modules you mentioned earlier, the ones that sometimes have those surprising negative coefficients?
Yeah, you start to see them for some of the Weyl group elements in type A2. The MW is expressed as a combination of Weyl modules, not just a single module.
Okay, so as things get more complex, we need more intricate expressions to capture what's going on. Can you give me an example of one of these combinations?
Sure. For the Weyl group element S1, S2 in type A2, the MW is VQ2, 1 minus VQ3 colleges. Those are specific Weyl modules labeled by their highest weights.
I see. So we're building the MW from these Weyl modules, combining them in ways determined by the Weyl group element.
Exactly. And as we go to more complex types like A3, B3, and beyond, the expressions for MW get even more complicated.
You mentioned they use SageMath to handle those tougher calculations. Why was that necessary?
Well, doing all the algebra by hand to define and express these MW can get pretty tedious and error-prone. SageMath allows mathematicians to automate a lot of those computations and explore a wider range of examples without getting bogged down in the details.
So it's like having a super-powered calculator that can handle all the heavy lifting, letting the mathematicians focus on the bigger picture. What did they learn from these computations?
Well, they were able to get those explicit expressions for the MW in terms of Weyl modules for types B3, A4, B4, and D4. Not only did those computations verify their general formula in these more complex cases, but they also revealed some cases where Lustig's conjectures didn't quite hold up.
Ah, right, those counterexamples we were talking about earlier. Can you tell me more about those? What kind of surprises did they find?
One of the most striking counterexamples is in type A4. Remember that symmetry Lustig predicted in the dimension polynomials? Well, it turns out it doesn't always hold. They found a specific MW whose dimension polynomial breaks that expected symmetry.
So Lustig's intuition, which seemed to work well for smaller groups, didn't quite generalize perfectly to all cases. What does that tell us about these MW elements?
It just shows how complex and subtle they really are. Even well-established conjectures can be overturned by new discoveries. That's what makes math so exciting.
Absolutely. It's the thrill of the unknown, the possibility of being surprised. What other counterexamples did they uncover?
Another one that stands out is in type B3. Remember Lustig's positivity conjecture? The idea that these MW should represent actual representations with all positive coefficients.
Right, he believed these MW would be built from Weyl modules in a positive, constructive way.
Exactly. But in type B3, they found an MW that breaks that rule. It has negative coefficients.
So another one of Lustig's conjectures bites the dust. It seems these MW are full of surprises, constantly challenging our expectations.
I know, right? It's like they're playing hide and seek with our intuition.
Speaking of playing games, you mentioned that the researchers also looked into the uniqueness of their MW elements. What did they find there? Were they able to prove that their solution was the only possible one? Or could there be other MW out there hiding in the mathematical shadows?
That's the million-dollar question, isn't it? They focused specifically on the group SL, which is a type of matrix group, and what they found was quite remarkable. For SL, where n is less than or equal to 5, they proved that any alternative solutions, if they exist, can only have dimensions that differ from their MW dimensions by a constant.
So even if there are other solutions out there lurking in the mathematical wilderness, they would have to be very close to the ones that researchers already found, at least in terms of their dimensions.
Precisely. It really points to the idea that their MW elements capture something fundamental about this problem. And get this, for SL5, they were able to completely rule out any other potential solutions that would satisfy all of Lustig's conjectures, including those related to symmetry and positivity.
Wow, so in that case, for SL5, their MW is the undisputed champion, the one true solution to this mathematical puzzle.
You got it. It's a powerful result that highlights the strength of their approach. They didn't just stumble upon a solution, they found the solution.
This deep dive has been incredible. We've gone from this abstract concept of reduction mod P to diving deep into these intricate MW elements, uncovering their surprising properties, and even proving their uniqueness in certain cases. It's been a wild ride.
Absolutely. And remember, we're not finished yet. We still have that intriguing connection to exceptional collections to explore. That's where things get really mind-bending.
I can't wait. It sounds like we're about to uncover another hidden layer of connections in the vast mathematical universe.
You're in for a treat. This is where the research paper takes us beyond the familiar and into a whole new realm of mathematical structures.
Okay, I'm ready to explore that connection to exceptional collections. It sounds like we're about to enter a whole new dimension of mathematics.
We are. This is where the research paper takes a really fascinating turn, moving into the realm of derived categories. They're powerful tools for understanding relationships between objects in a category.
You described derived categories earlier as a complex web of connections, like a map of a subway system.
That's a good analogy. Now, imagine you find special hubs in that subway system, strategically placed stations that make navigating the entire network much more efficient. That's kind of what exceptional collections are like in a derived category.
So they're like special sets of objects that help us organize and understand the whole category more easily. What makes them so exceptional?
They have certain properties that make them really useful for understanding the structure of the derived category. It's a bit technical to get into all the details, but basically they act like a basis for the derived category, allowing us to break down complex objects into simpler pieces.
Okay, I could see how that would be a powerful tool. So how do these exceptional collections connect to the MW elements we've been talking about?
Well, the amazing thing is that the researchers found a potential link between their SW elements, which we've been exploring in the world of representation theory, and a specific exceptional collection that was constructed by Samokin and van der Kollen.
Wow, that's incredible. It really is like finding a hidden tunnel connecting two seemingly unrelated subway lines.
Precisely. It hints at a deeper connection between representation theory and derived categories than we previously understood. Like these two areas of mathematics are talking to each other through this hidden passage.
What are the implications of finding this connection? Does it change how we view these areas of math?
It definitely opens up exciting new avenues of research. It suggests that techniques from one area could be applied to the other, potentially leading to new discoveries and a more unified understanding. For example, tools from derived categories might help us study representations, or insights from representation theory could shed light on the structure of derived categories.
It's like having a new set of tools and a fresh perspective to tackle those really challenging problems. What's the specific exceptional collection that they connected to the MW elements?
It's called the Samucken-van der Kallen Exceptional Collection, and it lives in the derived category of coherent sheaves on a partial flag variety.
Okay, I'm familiar with flag varieties, but could you remind us what those are and what these coherent sheaves represent?
Sure. A flag variety is a geometric object that describes a collection of nested subspaces of a vector space, like a chain of subspaces, each contained within the next.
Right, I remember now. What about these coherent sheaves? They sound a bit abstract.
Coherent sheaves are mathematical structures that we use to study geometric objects like flag varieties. They're a way to capture information about functions and sections on the variety, sort of like describing its local behavior.
So this exceptional collection gives us a way to organize and study these coherent sheaves on a partial flag variety.
Exactly, and the researchers suggest that this specific collection is intimately connected to their MW elements, particularly when we're dealing with representations that arise from these partial flag varieties.
It sounds like they're saying there's this deep connection between the algebraic world of representations and the geometric world of flag varieties, and this exceptional collection is the bridge between them.
That's a fantastic way to put it. It's like discovering a mathematical Rosetta Stone, allowing us to translate between these different mathematical languages and revealing a hidden unity underneath.
This deep dive has been an incredible journey. We've explored everything from the basic idea of modular reduction to these incredibly complex MW elements. We've encountered surprising counterexamples, unexpected connections, and now this amazing link to derived categories and exceptional collections.
It's been a whirlwind tour through some really fascinating areas of mathematics. And what's even more exciting is that this research opens up so many new avenues for investigation. It invites mathematicians to explore these connections further, look at new types of groups, and continue unraveling the mysteries of these complex mathematical structures.
It's like they've handed us a treasure map, leading to uncharted territories in the vast world of mathematics. Who knows what other hidden treasures and breathtaking landscapes are waiting to be discovered?
Exactly. So to all our listeners out there, stay curious, embrace the complexities, and don't be afraid to venture into the unknown. There's a whole universe of mathematical wonders out there waiting to be explored.
And on that note, we'll wrap up this deep dive. But remember, the journey of mathematical discovery never truly ends. Keep asking questions, keep exploring, and most importantly, keep that spark of curiosity alive.